Today we're going to have a walkthrough of your determination of an equilibrium constant lab. Now we started out with iron 3 plus in an aqueous solution reacting with thiocyanate to form an iron thiocyanate complex. Our iron thiocyanate is producing a reddish brown color. It's going to act as our chromophore, that's what we're measuring the absorbance of. And shown below is our expression for our equilibrium expression. We are looking at iron thiocyanate over the multiplication of iron 3 plus and thiocyanate. The equilibrium concentrations are inserted into this equation so that we can calculate our KEQ value. An important note, we can't plug in our initial concentrations. We have to plug in the equilibrium concentrations, which we'll be calculating in a few minutes. Okay, care of your lab mates. We've got some absorbance data from part 1 of the lab. The goal of part 1 was to find a relationship between the concentration of our chromophore, our iron thiocyanate complex, and absorbance. So to start out, because we have absorbance data, we need to calculate, to go with that, some concentration data for our iron thiocyanate. So we need to fill in this indicated column here. And we're going to do that using the equation shown below. We're going to take the initial concentration of thiocyanate, multiply it by the volume of thiocyanate used, and divide it by the total volume. So plugging in our values, we're going to get 2 mils of our thiocyanate solution, which was 0.0002 molar in concentration, and divide it by the total volume of 15 mils. Our milliliters are going to cancel out, yielding 2.7 times 10 to the minus fifth for our concentration of iron thiocyanate for trial A. Now that was for part 1. We're going to continue this calculation for trials B, C, and D for part 1, and that will fill out our chart nicely for our concentrations, and we now have concentration and absorbance data for part 1. We're going to create our plot using the concentration of iron thiocyanate complex for X and absorbances for our Y's. And keep in mind this is sample data, so it should be relatively close to what you got, while it shouldn't be exactly what you got. Alright, now here's our plot. It should be a scatter plot with a best fit line. We're going to have absorbance data on the y-axis, concentration of our chromophore on the x-axis, and our best fit line is going to reflect the relationship between those two values. So now that we have our calibration line and we can relate our absorbance data to our concentration data, we want to find equilibrium concentrations of our iron thiocyanate complex, our iron 3 plus, and our thiocyanate. Once we have equilibrium concentrations of these different species, we can calculate our equilibrium constants for each trial. Our end goal is to find the average standard deviation and percent error for all 5 trials worth of equilibrium constants. So we're going to have 5 equilibrium constants when we're done to work with. Well, we first want to start out by finding the equilibrium concentrations of our iron thiocyanate complex. We have absorbance data from part 2 for 5 different trials. We're going to convert this absorbance data to the concentration of our chromophore iron thiocyanate using the best fit line equation that we got from the plot that we made in part 1. A sample line equation is given below. This was my best fit line. Y represents our absorbance, so I've gone ahead and written absorbance in, and our X was concentration, so again I went ahead and wrote that in also. You're going to plug in the case of the sample data, 0.106 for your absorbance and solve for concentration. That would represent the concentration of our iron thiocyanate at equilibrium for trial 1. You would want to repeat that for trials 2 through 5 also, so we have equilibrium concentrations of our iron thiocyanate complex. We also need equilibrium iron concentrations. So in the equation below, we can calculate, once we have our iron thiocyanate equilibrium concentrations, our iron equilibrium concentrations. Okay, the values that we found for trials 1 through 5 for our equilibrium iron thiocyanate concentrations are found in red in the equation below, We'll solve this once for each of the 5 trials. But we also need the initial concentration of iron that we started out with. That's shown in blue below. And we're going to calculate this using the equation. Our iron 3 plus initial concentration is going to equal the concentration of the solution that we started with, 0.0020 molar, multiplied by the volume that we used in trial 1, which is 5 mils, divided by the total volume of the trial, which was 10 mils, results in an iron 3 plus initial concentration of 0.0010 molar. Now, our initial iron 3 plus concentration is the same for every trial, so we only need to calculate this once. We also need to find the equilibrium thiocyanate concentration. Now, since we've already calculated our value in red for each trial, our equilibrium concentration for the iron thiocyanate, we have values to plug in for each trial, but we also need initial concentrations for thiocyanate, which are shown in blue. So we're going to calculate this again by using a dilution equation. Our initial thiocyanate concentration is going to equal the concentration of our stock solution, which is 0.0020 molar. We multiply that by the 1 milliliter that we used, and divide by the total volume of that first trial, which was 10 mils. Our milliliters cancel. We would plug our resulting value in for our initial concentration of thiocyanate. Now, because the volume of thiocyanate that we used with each trial changed, we're going to need to calculate this value for each trial, so we'll have 5 different values depending on the trial for each of our 5 Part 2 trials. Alright, we have enough data to calculate now our equilibrium constants. For trials 1 through 5 of Part 2, we have equilibrium concentrations for our iron thiocyanate complex, which we got from our best fit line and solving that. We got our equilibrium concentrations of iron 3 and iron thiocyanate by manipulating our values in those last 2 sets of calculations that we did. So we can start plugging in our equilibrium concentrations for each trial and solving for a KEQ for each of the 5 trials. You want to find an average of these KEQ values, find your standard deviation, and find your percent error based on the true value of 169. Keep in mind, if you're less than 10% for your percent error, you are considered accurate. So thanks guys, hope this helped out.